Something unusual appears when astronomers study the motion of galaxies. At first glance, you would expect galaxies to simply drift apart as the universe expands. And for the most part, that is exactly what happens. But hidden within the data is a pattern that doesn't completely fit that picture. The Milky Way is not merely moving along with the general expansion of space. It is traveling toward a specific region of the cosmos, and it is far from alone. Thousands of nearby galaxies and entire galaxy clusters seem to be heading in the same direction, not because of cosmic expansion, but because of something else, something with gravity. Whatever is causing this motion cannot be clearly seen, and it is not located where astronomers originally expected to find it. Yet its influence appears to extend across enormous distances, affecting galaxies throughout our cosmic neighborhood, including our own. If the universe expanded in a perfectly uniform way, galaxies would gradually move away from one another according to predictable mathematical rules. This idea was first demonstrated by Edwin Hubble nearly a century ago and remains one of the foundations of modern cosmology. However, a closer look revealed a complication. As observational techniques improved, astronomers discovered that the motions of many galaxies did not perfectly match the values predicted by expansion alone. The numbers simply did not add up. Certain galaxies appeared to possess an additional motion layered on top of the overall expansion of the universe. It was as though something unseen was pulling them toward a common destination. Imagine standing beside a river. You expect the water to flow steadily downstream, but then you notice patches of water drifting sideways, caught in invisible currents beneath the surface. That is remarkably similar to what astronomers observed in the local universe. The Milky Way was not merely floating with the cosmic current, it was moving with a measurable velocity toward a particular area of the sky. This discovery emerged from detailed surveys of galaxies and galaxy clusters during the 1970s and 1980s, led by researchers such as Brent Tully and Alan Dressler. They measured galactic redshifts, the stretching of light caused by cosmic expansion, to determine how fast galaxies should be receding. Then they compared those calculations with independent distance measurements obtained through methods involving objects such as Cepheid variable stars. The discrepancy became impossible to ignore. Expansion alone could not account for the observed velocities. Many galaxies possessed what astronomers call peculiar velocity, a component of motion generated not by the expansion of space itself, but by gravitational attraction. That realization transformed a curiosity into a mystery. These peculiar motions were not random. Instead, they appeared to point in roughly the same direction, as if an enormous unseen gravitational source were drawing entire clusters of galaxies toward a hidden concentration of mass somewhere beyond our view. When astronomers traced the motion of these galaxies, it pointed toward a region of the sky hidden behind the dense plane of the Milky Way. It is an area notoriously difficult to study because it is crowded with stars, dust, and gas. What could possibly be concealed there? Long before scientists understood its true nature, they gave this mysterious influence a name: the Great Attractor. It appeared to be a vast concentration of mass capable of altering the trajectories of galaxies across hundreds of millions of light years. And perhaps the most fascinating detail is that our own galaxy is caught in this cosmic flow as well. So what exactly is pulling us? The name Great Attractor might suggest something obvious: a gigantic black hole, or an enormous cluster of galaxies glowing brightly in X-rays. Yet the reality turned out to be far more complicated. The source was not immediately visible. In fact, it could not be clearly observed at all. When researchers first detected these unusual motions, they expected a straightforward solution. Point a telescope at the source, identify a massive object, take measurements, add it to the catalogs, and solve the mystery. That did not happen. Instead, they encountered a major obstacle. The region from which the gravitational pull seemed to originate lies behind the thick disk of the Milky Way. Billions of stars, immense clouds of dust, and vast quantities of gas make our galaxy spectacular to look at, but they also block our view of what lies beyond. This hidden section of the sky became known as the zone of avoidance, not because it is empty, but because traditional optical telescopes struggle to see through it. Yet despite being concealed, something beyond this barrier was influencing galaxies across enormous cosmic distances. To investigate further, astronomers changed their approach. Rather than relying solely on visible light, they turned to radio observations, infrared surveys, and X-ray astronomy, forms of radiation capable of penetrating regions obscured by dust. Radio waves pass through interstellar gas and reveal the distribution of neutral hydrogen within galaxies. Infrared observations expose cooler dust clouds and stellar structures hidden from ordinary telescopes. X-rays, meanwhile, highlight extremely hot plasma filling the space between galaxy clusters, with temperatures reaching millions of degrees. Piece by piece, a clearer picture began to emerge. What they uncovered was not a single object. The Great Attractor is neither a planet, nor a star, nor even a supermassive black hole. Instead, it is best understood as a vast gravitational concentration, a region where matter is packed much more densely than average. It consists of numerous galaxy clusters and superclusters interconnected within an exceptionally dense section of the cosmic web. One of its major components is the Norma cluster, a massive collection of galaxies located roughly 220 million light-years away. But this is only one part of a much larger structure. There is also the Norma wall, an immense filament of galaxies stretching across space. Beyond that lie additional structures, including the Centaurus cluster, the Hydra Centaurus supercluster, and several other large-scale concentrations of matter, all gathered within the same general region of the universe. Together, these colossal structures create a powerful gravitational influence that shapes the motion of galaxies across an enormous volume of space and contributes to the phenomenon we call the Great Attractor. At this point, you might be wondering, if we cannot directly observe most of it, how do we know it exists at all? That is a fair question. The answer lies in the motions of galaxies. Imagine trying to figure out the shape of an object hidden beneath a blanket. You cannot see the object itself, but you can tell where it is by the way the fabric bends, stretches, and folds around it. The universe works in a similar way. In this analogy, space itself is the blanket, while the unusual motions of galaxies are the folds and distortions that reveal where the hidden mass is located. When astronomers observe countless galaxies drifting toward the same region of space, the conclusion is difficult to avoid. Something extremely massive must be influencing them. But even this picture is more complicated than it first appears. The Great Attractor is not a single, well-defined object in the way many people imagine. Instead, it is better described as a gravitational focal region. It is not necessarily a destination that everything is falling toward, but rather an area where gravity exerts an unusually strong influence on our local cosmic neighborhood, and it may not even be the dominant source of that pull. Later discoveries suggested that even larger structures such as the Shapley supercluster located beyond the Great Attractor could be contributing an even stronger gravitational influence. In other words, what we call the Great Attractor may simply be one feature within a much larger gravitational landscape that astronomers had not yet mapped when the term was first introduced. So when we say that our galaxy is being drawn through space, it is not heading toward a single gigantic object. Instead, it is responding to an enormous network of structures, galaxy clusters, superclusters, cosmic walls, filaments, and likely vast quantities of dark matter that remain invisible to our instruments. The Great Attractor is merely the first major feature of that landscape that scientists were able to identify. Perhaps the most intriguing aspect is that we still do not know its full extent, or where its influence truly ends. You have probably heard that the universe is expanding. Galaxies, on average, are moving farther apart because space itself is stretching over time. That is absolutely correct. However, it is only part of the story. While expansion dominates on the largest scales, gravity continues to shape the universe on smaller scales, pulling matter together wherever enough mass is concentrated. In the case of the Great Attractor, that gravitational pull is strong enough to partially overcome the effects of cosmic expansion within our region of space. A simple example helps illustrate the idea. Imagine a balloon covered with dots. As the balloon inflates, every dot moves farther away from the others. This represents the expansion of the universe. Now imagine that some of those dots are connected by elastic threads. As the balloon grows, the connected dots do not separate as quickly because the threads pull them toward one another. Those threads represent gravity. Now extend this concept to the cosmos. The Milky Way is not isolated. It belongs to a vast web of galaxies, groups and clusters that continuously influence each other's motion through gravity. And in our corner of the universe, there is a clear direction toward which much of this motion appears to be flowing, a direction associated with the massive region known as the Great Attractor. The process is not a simple straight-line journey. It is more like a cosmic tug-of-war. On one side, the expansion of the universe pushes galaxies apart. On the other, the immense gravitational well created by the dense structures surrounding the Great Attractor pulls matter inward, drawing our galaxy and countless others along with it. Astronomers refer to this phenomenon as a peculiar velocity. It is motion that cannot be explained by the overall expansion of the universe alone, but instead arises from the gravitational influence of nearby structures. In our case, the local group, which includes both the Milky Way and the Andromeda Galaxy, is traveling at roughly 600 kilometers per second in a specific direction relative to the cosmic microwave background. And we are far from alone. Numerous neighboring galaxy groups and clusters are moving in much the same direction, like leaves drifting within a broad and persistent cosmic current. But the story becomes even more fascinating. The gravitational pull affecting us is not generated by a single source. It is shaped by everything around us: galaxy clusters, filaments of matter, vast cosmic voids, dark matter halos, and other large-scale structures that collectively influence how galaxies move through space. Some regions contain greater concentrations of matter and therefore exert a stronger gravitational pull. Other regions are comparatively empty, and those enormous voids can effectively redirect the motion of galaxies away from them. So, this is not simply a journey toward one destination. It is movement through a complex gravitational landscape filled with peaks, valleys, currents, and hidden influences that scientists are only beginning to fully understand. And this is where dark energy enters the picture. While gravity works to draw matter together, dark energy acts in the opposite direction, driving space itself to expand. More importantly, that expansion is accelerating. As billions of years pass, the universe stretches faster and faster, making it increasingly difficult for gravity to keep distant structures bound together. The balance between these forces is remarkably delicate. For now, within our local region of the cosmos, gravity still dominates. That is why our galaxy and its neighbors continue moving toward the region associated with the Great Attractor. However, on much larger scales and over immense periods of time, dark energy may ultimately gain the upper hand. Galaxies that are not gravitationally bound to one another could eventually drift so far apart that they will never interact again. This means the situation is far more complicated than a simple attraction toward a giant object. We are not spiraling into a single destination like water disappearing down a drain. Instead, we are following pathways carved by gravity and mass, while the fabric of the universe itself continues to expand around us. A useful analogy is walking on an escalator that is simultaneously stretching outward in every direction. And here is the part that truly changes the perspective. The Great Attractor is not pulling galaxies inward like a giant cosmic vacuum cleaner. In fact, there is a good chance we will never actually reach it. It is even possible that some of the most important effects of its influence are already behind us. What we are observing today is largely the consequence of that gravitational pull rather than a direct journey toward its center. It is the result of existing within a region of space where matter has been flowing in roughly the same direction for an extraordinarily long time. So yes, our galaxy is moving. Yes, enormous concentrations of mass are helping to shape that motion, but at the same time, the universe is expanding ever faster, carrying distant regions farther apart. This is not a race. It is not a destination. It is motion within a cosmic system that is constantly evolving and reshaping itself. At first glance, it is tempting to think of the Great Attractor as the ultimate gravitational ruler of our neighborhood, the unseen force pulling the strings behind everything. But there is a twist. It is not the only player involved, and it may not even be the most influential force guiding the motion of our galaxy through the cosmos. The farther astronomers expanded their view of the cosmos, the more obvious it became that the Great Attractor was not the final answer. It was only one feature within a much larger and more complex structure. To understand what is really happening, we need to look at the bigger picture. In 2014, researchers fundamentally redefined our understanding of the local universe. Rather than mapping only where galaxies are located, they also tracked how those galaxies move through space. What emerged was a remarkable pattern. Countless galaxies, including our own, appeared to flow along interconnected pathways, much like streams joining together to form an enormous river. That immense cosmic river is now known as the Laniakea supercluster. Laniakea is enormous beyond ordinary comprehension. Stretching across more than 500 million light-years and containing over 100,000 galaxies, it includes the Milky Way, the region associated with the Great Attractor, the Virgo cluster, and many other major cosmic structures. Instead of viewing galaxy clusters as isolated islands scattered through space, Laniakea reveals them as parts of a single interconnected system. The motion we observe is not caused by one dominant object pulling everything toward itself. Rather, galaxies move along vast gravitational gradients that extend across hundreds of millions of light-years. Within this framework, the Great Attractor is simply one particularly dense region, a bend in the current rather than the source of the flow itself. But the story becomes even more intriguing. In 2017, scientists introduced another concept that shifted the discussion. Perhaps our motion is not determined solely by attraction. Maybe part of it is caused by something that appears to do the opposite. Researchers identified evidence suggesting that a significant component of our movement may result from an enormous region containing remarkably little matter, a giant cosmic void. This structure became known as the dipole repeller. At first glance, the idea sounds counterintuitive. Gravity pulls, it does not push. Yet the explanation lies in gravitational imbalance. When one side of space contains a dense concentration of matter and the opposite side contains a vast underdense region, the resulting effect can resemble a push away from the emptier area and a pull toward the denser one. The void is not actively repelling anything. Instead, there is simply less gravitational influence there to counteract the attraction coming from elsewhere. Imagine standing between a solid wall and a cliff edge. The wall does not push you forward, but the absence of support behind you makes movement toward the open side much easier. According to this interpretation, the dipole repeller plays an important role in shaping the peculiar velocity of our local group. Together with the pull of the Great Attractor, it helps explain the large-scale dipole pattern observed in the cosmic microwave background. Interestingly, the dipole repeller lies in roughly the opposite direction from the Great Attractor. A useful way to picture the situation is this. Dense structures such as the Great Attractor and the Shapley supercluster draw us forward, while the enormous void behind us effectively releases its gravitational hold. The result is a cosmic push and pull operating across distances that are almost impossible to visualize. This realization highlights something often overlooked. Cosmic voids are not merely empty gaps between galaxies. They actively shape the architecture of the cosmic web. By influencing the movement of matter on vast scales, they can guide large-scale flows almost as effectively as galaxy clusters themselves, and may even affect the behavior of cosmic expansion across regions approaching 1 billion light-years in size. And the story does not end there. Additional clusters, massive galaxy walls, and enormous filaments are all woven into this gravitational network. Space is far from empty. It is threaded with hidden pathways that channel the movement of galaxies, much like highways direct traffic across a continent. The Great Attractor may be the structure that captured our attention first and earned a memorable name, but it is only one participant in a much larger cosmic system that continues to shape the journey of galaxies across the universe. The motion of our galaxy is not defined only by where we are heading, but also by where we are coming from. We are effectively caught in a gravitational tug-of-war between dense cosmic structures and vast empty voids. The direction we move in today is the outcome of this long and intricate interplay of forces. There is no single cause, no single destination. Instead, there is a combination of invisible influences stretching across space, guiding us through a web of structure that we can barely perceive. Despite all the progress in astronomy, the Great Attractor remains one of those mysteries that refuses a simple explanation. We know it is there. We observe the motion it influences. Yet the details, what it truly is and how far its influence extends, remain frustratingly out of reach. The first uncertainty is its actual scale and mass. Some estimates suggest it may correspond to the mass of tens of thousands of Milky Way-like galaxies. Others argue that the observed motion is not dominated by the Great Attractor alone, but also by even larger structures at greater distances, such as the Shapley supercluster. The difficulty is that the farther we look, the harder it becomes to disentangle overlapping gravitational influences. It is like standing in a crowded stadium trying to identify a single voice while everyone is shouting at once. A second layer of uncertainty comes from dark matter. We can observe galaxies, clusters, and hot intergalactic gas, but this visible matter is not enough to account for the gravitational effects we measure. A significant part of the Great Attractor's influence is therefore likely tied to dark matter, the invisible scaffolding that makes up most of the universe's mass. We do not know how it is distributed in this region, how dense it is, or whether it forms a smooth concentration or something far more irregular. In a sense, we are sketching the outline of something we cannot see directly, hoping our indirect measurements are correct. And finally, there is a deeper question. Is the Great Attractor even a true destination? The name suggests a single point we are inevitably falling toward, but cosmology is more complicated than that. Because the universe is expanding at an accelerating rate due to dark energy, it is entirely possible that we will never reach it in any meaningful sense. The pull we observe today may simply be part of a larger flow that will eventually be overtaken by cosmic expansion. In other words, we may not be falling into the Great Attractor at all. We might just be passing by it on a trajectory towards something beyond. Even the so-called zone of avoidance continues to limit what we can observe. Despite radio and X-ray surveys, important details remain hidden behind the Milky Way's dense disk. New sky surveys keep revealing previously obscured galaxies, and each discovery subtly reshapes the overall picture. The Great Attractor may not be a single coherent structure, but rather a layered region of overlapping densities, each contributing to the overall gravitational pull. A broader uncertainty remains. How do we define the boundaries of something like this at all? Galaxies have shapes. Black holes have event horizons. But the Great Attractor is different. It behaves more like a gradient than a distinct object. Where does it begin? Where does it end? How do we separate its influence from neighboring superclusters and cosmic voids? These are not minor details. They go to the core of how we map the universe and describe its structure. So, we are left with a paradox. We know enough to be certain that the Great Attractor exists, yet not enough to fully describe it. It is real. It is influential. It shapes our motion. And yet, the closer we examine it, the more it dissolves into the broader cosmic web. It is easy to hear about something like the Great Attractor and think, fine, there is a massive region pulling galaxies around. But the real significance goes far beyond motion. It is about the architecture of the universe itself. Understanding why our galaxy moves the way it does leads directly into deeper questions about structure, gravity, and the fundamental composition of the cosmos. Most importantly, this motion reveals the unseen. We do not observe dark matter directly. We do not see gravity as a physical form, but we do observe how galaxies respond to it, their directions, their velocities, their deviations from uniform expansion. These patterns are not just numbers, they are clues. When thousands of galaxies drift toward a single region, it implies something massive lies there, even if it emits no light. This is how we map dark matter, not by seeing it, but by tracing its gravitational fingerprints. This is why peculiar velocity is so important. It represents motion beyond the uniform expansion of space. It reveals the terrain of the gravitational landscape, its slopes, valleys, and hidden wells. Cosmic expansion stretches space evenly, while gravity introduces distortions. By measuring those distortions, we effectively reconstruct a map of the universe's hidden mass distribution. No telescope can see it directly, but galaxy motion can reveal it. On the largest scale, the universe is not a random scattering of galaxies. It has structure, a vast cosmic web of clusters, filaments, walls, and voids. It is not perfect or symmetrical, but it is far from chaotic. These large-scale flows of galaxies toward overdense regions, such as the Great Attractor or the Shapley supercluster, reveal hidden order. They show that we are part of a structured system, one that records the history of how matter evolved since the early universe. This perspective also places our own galaxy in a broader context. We tend to think of the Milky Way as a fixed home drifting through space, but it is anything but stationary. It is part of a chain of motions extending far beyond what we can directly perceive. It orbits within the local group, which moves toward the Virgo cluster, which itself is drawn into the flow toward the Great Attractor, which may in turn be influenced by even larger structures beyond it. Each motion is layered on top of another, none of them isolated. Every flow, every attraction, and every repulsion reshapes the large-scale structure of the cosmos. Even galaxy collisions, mergers, and dispersal patterns depend on these enormous gravitational currents. Understanding the Great Attractor is therefore not just about a single direction of motion, it is about the dynamics of cosmic evolution itself. There is also a philosophical undertone to all of this. We are not standing still, yet we are not moving randomly either. We are carried by a current we did not choose and cannot escape, and we are only beginning to understand how deep and complex that current truly is. This matters because it reminds us that the universe is not static. It does not simply exist, it evolves. Everything is in motion, shaped by forces we are still learning to understand. And if we want to uncover the true architecture of the cosmos, we cannot ignore these flows. They are not noise, they are the signal.